When Pluto was officially reclassified as a dwarf planet in 2006, many people quickly dismissed it as a forgotten, icy remnant at the edge of our solar system. Once celebrated as the ninth planet, it was suddenly relegated to the status of a distant, frozen rock, a cold and quiet world thought to hold little scientific significance. However, that perception has been changing in remarkable ways, particularly due to new high-resolution images and data from the James Webb Space Telescope, JWST. Pluto is no longer viewed as a silent, lifeless body. Instead, it is emerging as one of the most mysterious and intriguing objects in our solar system. The visuals and data returned by JWST have challenged many long-held assumptions about Pluto, once thought to be geologically dead. The dwarf planet now appears to conceal something far more complex beneath its icy surface, something that could fundamentally reshape our understanding of the potential for life beyond Earth. At the center of this intrigue lies Pluto's most iconic feature, Sputnik Planitia, a vast, heart-shaped glacier that has captured the attention of scientists and space enthusiasts alike. Composed largely of frozen nitrogen, this enormous icy plain is not just visually striking, it plays a critical role in Pluto's geology. Its mass is so significant that it affects the planet's rotation and gravitational balance, almost as if Pluto is weighted more heavily on one side. Even more compelling is what may lie beneath Sputnik Planitia. Scientists believe that below its thick frozen crust, there could be a subsurface ocean, a vast reservoir of liquid water, kept from freezing solid by heat generated from radioactive decay within Pluto's rocky core. Despite being nearly 6 billion kilometers from the Sun, this internal heat may be enough to maintain liquid water under the surface. This possibility redefines Pluto not as a frozen wasteland, but as a dynamic and evolving world. If such an ocean does exist, it raises the profound possibility that Pluto might support some form of life. Far from being a barren ball of ice, Pluto could harbor conditions conducive to biology, albeit in an environment radically different from Earth. The presence of liquid water, a fundamental ingredient for life as we understand it, in such a remote part of the solar system opens up new horizons for astrobiology. Wherever water is found, the potential for life follows closely behind. Supporting this theory are clear signs of geological activity. NASA's New Horizons mission, which performed a flyby of Pluto in 2015, revealed a surface marked by fault lines, ridges, and tectonic fractures, features commonly associated with active worlds. These structures suggest that Pluto's interior is not dormant, but continues to reshape the icy shell above it. Pluto's largest moon, Charon, further deepens the mystery. Unlike most planetary moon systems, Pluto and Charon are gravitationally locked in a binary orbit, each body circling a shared center of mass that lies in space between them. This gravitational interaction creates tidal forces that cause internal friction within Pluto's crust and potentially within its suspected subsurface ocean, generating heat and motion. Though still not fully understood, these forces may be crucial in maintaining Pluto's geological and possibly even biological activity. Some researchers have gone further, speculating about the existence of microbial life beneath Pluto's icy shell. These hypothetical organisms would need to be uniquely adapted to conditions of extreme darkness, high pressure, and bitter cold. If such life exists, it would have evolved in total isolation, protected from solar radiation by thick layers of ice. According to physicist Brian Cox, discovering microbial life in such an extreme environment would dramatically alter our understanding of biology and the conditions under which life can exist across the universe. Adding to the intrigue are unusual heat signatures and chemical markers detected beneath Pluto's surface by JWST. Though these patterns are not yet fully understood, they bear resemblance to those produced by biological processes on Earth. Some scientists have even considered the possibility, however speculative, that life on Pluto might not only exist, but could be radically different and potentially hazardous. Such life forms, if they exist, would likely challenge the very definition of life itself. One theory about Pluto's underground ocean suggests that it formed during the chaotic early history of the solar system. Pluto may have originated from a series of massive collisions and impacts that produced enough heat to melt its internal ice. Over billions of years, this internal warmth, sustained by radioactive decay, may have maintained parts of the interior in a liquid state. If this is true, Pluto has been geologically active since its formation, a world born of fire, encased in ice, and still alive deep below the surface. Pluto's thin but dynamic atmosphere adds another layer of complexity, composed mostly of nitrogen with traces of methane and carbon monoxide. This atmosphere forms a reddish haze due to organic molecules known as tholins, which are created when ultraviolet light from the sun interacts with the atmospheric gases. Tholins are considered potential building blocks of life, hinting at organic chemical processes occurring even in this distant region of the solar system. Charon, Pluto's moon, also displays signs of tectonic activity in its past. Its surface features deep chasms, ridges, and grooves, and its poles exhibit strange red caps. These may have formed from gases escaping Pluto, drifting through space, and freezing on Charon's surface. This eerie interaction between the two celestial bodies raises the question: could Pluto and Charon be influencing each other's geology, chemistry, or perhaps even biology? Pluto is unlike most other objects in the Kuiper Belt, a distant region of the solar system populated by icy remnants from its formation. While most Kuiper Belt objects are cold and inert, Pluto is full of surprising activity. Its moving glaciers, dynamic surface, hazy atmosphere, and internal warmth make it an outlier. If Pluto is this active, it begs the question: what other icy worlds beyond Neptune might also harbor subsurface oceans and hidden processes? While the James Webb Space Telescope has opened a new chapter in Pluto's story, many questions remain unanswered. The New Horizons mission provided only a brief but valuable glimpse. Future missions will need to return, perhaps to orbit Pluto, drill into its crust, analyze its atmosphere in greater depth, and directly explore the suspected ocean beneath. Each new discovery could bring us closer to understanding the origins of life, the history of the solar system, and our place within it. One particularly intriguing area still under investigation is the possibility of a magnetic field on Pluto. Though we lack direct evidence, some indirect observations suggest that magnetic activity may exist beneath the surface. If confirmed, a magnetic field could protect Pluto's atmosphere and subsurface ocean from solar radiation, just as Earth's magnetic field does. It might also help explain some of the strange geological features and unexplained heat signatures observed on the planet's surface. Pluto's remote location in the outer solar system subjects it to unique influences. Gravitational tugs from nearby Kuiper Belt objects and the occasional passing star may help stir its interior, maintaining the internal activity once thought impossible for such a small, distant world. Ancient impacts may have also contributed, reshaping Pluto's surface and leaving behind evidence still visible today. Once dismissed as a cold, dead rock, Pluto is now recognized as a world of puzzles, surprises, and potential. With its flowing glaciers, shifting ice, intriguing chemistry, and possible subsurface ocean, Pluto has earned its place as one of the most captivating objects in our solar system. It challenges conventional ideas about what constitutes a planet, what makes a world geologically alive, and where life might arise. The most important question may no longer be whether Pluto could support life, but what kind of life it might already contain. What secrets lie buried beneath its icy crust? What mechanisms keep this remote world active? And what else might be hidden in the far reaches of the Kuiper Belt, waiting to be discovered? Pluto, far from being a relic of the past, now stands as a symbol of the future, a reminder of how much we still have to learn and how many mysteries remain to be uncovered in the cosmos.